So, now that we've been talking about efficiency analysis, let's get our hands dirty and do some. We begin with the classic Towers of Hanoi, one of my favorites. Developed in 1883 by French mathematician Edouard Lucas, one of the puzzle's many colorful origin myths tells of an ancient Indian temple wherein a group of Brahmin monks tirelessly carry out the steps of the algorithm to move 63 disks from A to C. And it's said that when they finish, the world will end. So, for that reason alone, it's incumbent upon us to find the runtime of this algorithm. In case you're unfamiliar, the problem goes like this. You're given these 3 pegs, a set of n disks, and you have to move all the disks from one side to the other. The catch is that you may only move one disk at a time, and if a disk moves, it has to go to another peg, so I can't do this. And a larger disk cannot go on top of a smaller disk, so this I cannot do. For this exercise, I want you to build and solve a recurrence relation that'll tell us exactly how many moves it takes to solve the problem for any number of disks. Let's break down solving the problem for 3 disks, and then I'll set you loose on solving it for n. So how do I do this? Well, I can take this top one, move it from A to C. That's one move. And then this one, from A to our helper B. And then this first one again, from C to our helper B. And now I think you see the trick. This third one goes in one move all the way from A to our destination C. And then we just solve for these 2 again, but this time using A as our helper instead of B. And that's it. So how long did that take? How many moves? Well, let's break it down. It took 3 moves to solve for the top 2 disks to get them from A to our helper B. It took 1 move to move this third disk from A to C, and then 3 moves again to solve a second time for these 2 disks. So 3 plus 1 plus 3, 7. It took 7 moves. But how long would it take to solve for 4 disks? Or 5 disks? How about in general? How about for n disks? That I leave to you to solve, but I'll give you one quick hint. Let's count the moves for 4 disks. So how do we do this? Well, I'll tell you a trick. If our only goal is counting moves, then we already know how to solve for 3, so we're already done. What do I mean? Well, first we solve for the top 3 disks. We get them to be via our new helper C. Let's assume we spend 7 moves doing that. Now we solve for the 4th disk, which is just 1 disk, so that's 1 move. We spend 1 move doing that. Then we solve again for these 3 using A as our helper instead of C. Assume we spend another 7 moves doing that. And we're done. So for 4 disks, we first spend 7 moves solving for the top 3, 1 move solving for the bottom 4th, and then another 7 moves solving for the top 3 again. And then we're done. 7 plus 1 plus 7, 15 moves for 4 disks. And that's your hint. I will see you in the solution. Welcome back. Let's build a recurrence relation. Recall that we showed how to reduce the problem of solving for 4 disks to that of solving for 3 disks, and solving for 3 reduces to solving for 2, and so on. Given that pattern, we can say that t of n-1 equals the steps required to move n-1 disks, and t of n likewise equals the steps required to move n disks. Now recall that we broke the problem for 4 disks down into 3 steps. First, solve for the top 3 disks, then solve for the bottom 1 disk, then solve one more time for the top 3 disks. Expressed in terms of n, we have t of n equals t of n-1, this is just the top 3 disks, or the top 2 disks, or what have you, plus 1, plus t of n-1, which we can simplify with a little algebra as 2 times t of n-1 plus 1. Okay, looking good. However, notice that our recurrence repeatedly calls itself on n-1. If left unchecked, it'll run indefinitely toward negative infinity. We can't have that. So we remedy this by recalling the simplest version of the problem to solve. And that's the case where n equals 1. It only takes one step to move one disk. So we'll call that our base case, and now we have t of n equals 2 times t of n minus 1 plus 1, with base case t of 1 equals 1. So now we have our recurrence and our base case. Not so bad, right? Now, let's apply the substitution method and see what we find. We'll start from our base case, one disk. T of 1 equals 1. Now we'll increment n by 1 to get our t of 2 for 2 disks. T of 2, inserting 2 for n, equals 2 times t of 2 minus 1 plus 1, which is just 2 times t of 1 plus 1. Let's add a third disk, this time substituting our t of 2 from up above. So we'll have t of 3 equals 2 times t of 2 plus 1, and we get our t of 2 from up here. We substitute it in t of 2 plus 1. And now why don't we go ahead and distribute that 2? Now let's add a fourth disk, incrementing n again, and substituting our t of 3 from up above. So we'll get t of 4 equals 2 times t of 3, so let's go grab that. And there it is, plus 1. And let's go ahead and distribute that too. Now, you're probably already noticing a pattern here. Let's go one more round to be sure. T of 5 equals 2 times t of 4, let's grab that. And there it is, plus 1, and let's go ahead and distribute our 2. Pattern confirmed. We've gone deep enough in our substitutions that I think we can safely make the following generalization about how this equation tends to look as the number of disks increases. And hey, we lucked out, because this isn't just any pattern, it's a geometric series. I say we lucked out because the solution to the geometric series is already known, so our problem just became trivially easy. The solution looks like this. Now notice that if we flip it around, our series looks almost exactly the same. We just have to subtract 1 from r's exponent on the right-hand side to balance it out. Finally, we know our r is just 2, so let's plug it in and see what our runtime is. We land on big O of 2 to the n because in big O notation, constants are dropped. Let's test this out to see if we're right. Remember earlier we saw it took 7 moves to solve for 3 disks? Well, let's plug in 3 and see if this worked. Let's take our function and move it over here. It checks out. So by completing this exercise, we've not only discovered the recurrence relation that governs our algorithm, we've determined its runtime, and can even calculate exactly how many steps it'll take to solve for any input size. To put it in practical terms, you're now able to determine for any size Hanoi puzzle whether the world will end before or after lunchtime.